You know, when you think about a falling apple, or a planet orbiting the sun, or even how a population grows, what if I told you there's a single mathematical language that describes all of that? Well, there is. And today, we're going to decode that hidden language of change.
So what is this hidden code, right? What's the secret? Well, it's this amazing mathematical framework that scientists, engineers, you name it, use to model, predict, and just understand how the world works. And the answer is actually pretty elegant.
And here it is. The answer is a differential equation. Now, at its core, it's just an equation that has derivatives in it. And derivatives is really just the math term for rates of change. So what's so cool about this is that it's not about what a value is right now, but how that value is changing second by second.
Okay, so to really get a handle on this language, we've got to learn to spot its different forms, kind of like its different dialects. It all comes down to classification, and trust me, this is the very first step to becoming fluent.
All right, first up, we've got ordinary versus partial differential equations. You'll hear them called ODEs and PDEs. And the difference? Super simple, actually. An ODE tracks change based on just one thing, usually time. But a PDE? Whoa, that handles change across multiple things at once, like how the temperature changes across both the length and the width of a hot metal plate.
Okay, next up, we classify them by their order. Now, I know that sounds super technical, but it's not, I promise. It's literally just the highest derivative you see in the equation. And the order is so important because it tells us how many layers of change we're dealing with.
Here's a super simple way to think about it. A first-order equation, that can describe a car's velocity, how fast its position is changing. But what if you want to talk about its acceleration? That's the change in velocity. For that, you need a second-order equation. See? More order just means more detail about what's changing.
And now for a really, really big one, linear versus nonlinear. This distinction is huge. Linear equations, they're nice. They're predictable, usually easier to solve. But nonlinear equations, oh boy, that's where things get wild. We're talking complex, even chaotic behavior. It's basically the difference between the simple swinging pendulum and trying to predict the weather. So how do you spot one of these nonlinear beasts in the wild? Well, here are your red flags. Are you seeing the function multiplying by its own derivative? Is the function raised to a power, like y squared? Or are you seeing crazy stuff like sine of y or e to the y? If you spot any of those, you've left the easy path and you are deep in nonlinear territory.
All right, so we've got the key characteristics down. Now let's grab our field guide and put this into practice. We're going to go out and identify a few of these mathematical species.
Okay, time for a little pop quiz. Look at this first one. It's got dy over dx, so just one variable. That's an ODE. Highest derivative is the first derivative, so first order. And nothing weird going on, so it's linear. Boom. How about the second one? See that y double prime? That's a second derivative, so it's a second-order linear ODE. And the last one? Aha! See the y prime squared? That's our red flag. It's a dead giveaway, so it's first order, but it's nonlinear. See? Once you know the rules, it's kind of like a puzzle.
Okay, so we can identify them, we can classify them. We're getting pretty good at this, but that leads to the really big question, right? What's the point? What are we even trying to do with all of this?
Yeah, exactly. So what's the end game here? When someone says solve this differential equation, what are we actually looking for? What's the prize at the end?
And this is maybe the most important thing to get. The solution. It isn't just a number, like 5 or 10. The solution is the entire function. We're hunting for that original formula, the original story, that y equals something something x, that follows the rules of change that the differential equations set up.
Now, sometimes, if we're lucky, we find that solution in a really nice, clean form. We call that an explicit solution. That's just when you can get y all by itself on one side of the equal sign. Y equals something.
So something like y equals x squared plus 1, that's a perfect example. It's so clean, right? You give me an x, I plug it in, and bam, I give you the y. It's as direct an answer as you could ever hope for.
But it's not always that easy. Sometimes the relationship is, well, it's more tangled up. An implicit solution is where we know there's a connection between x and y, but we can't easily get y all by itself. The function is kind of hidden or implied inside the equation.
And the classic example everyone learns is the equation for a circle. X squared plus y squared equals 25. I mean, that equation definitely describes a relationship between x and y, right? It draws a perfect circle. But y isn't just handed to you on a silver platter. You'd have to do some work to solve for it. It's implicit.
Okay, so this is where things get really, really cool. It turns out that a single differential equation, it doesn't just describe one single answer. Nope, it often describes a whole family of possible answers.
We call this a general solution, and you'll notice it has this extra letter in it, usually a C, for constant. Think of C as a dial you can turn. For every different value you pick for C, you get a whole new function, a different curve, but every single one of them perfectly solves the original equation. It's amazing, a whole family of solutions from one set of rules.
But a whole family of solutions can feel a little vague. What if we know more? What if we don't just know the rules of the story, but we also know exactly where the story begins?
That starting point, that's what we call an initial condition. And once you have that, everything changes. It lets you solve for that C, to lock it into a specific number. And when you do that, you no longer have a general solution, you have a particular solution. You've gone from an infinite number of possible stories to the one story that is happening right here, right now.
And believe me, it gets even bigger than this. We don't have to stop with just one equation. We can build entire systems of these things to model how multiple parts interact all at once. Think about predator and prey populations, how they rise and fall together, or super complex chemical reactions. This language scales up to describe almost anything.
So, we've uncovered this incredibly powerful language for describing change in the universe. It feels like we can write an equation for just about anything. But that leads to one last really deep question. Just because you can write down the equation, does that guarantee a solution even exists? And if it does, is there only one? Now that is something to chew on.